Perhaps the most remarkable fact about the universe, if you think about it on a truly fundamental level, is that it exists at all. And yet, not only does it exist, but there's matter within it which obeys the same rules everywhere and at all times. It assembles according to the physical laws governing reality to create, among other things, atomic nuclei, neutral atoms, molecules, stars, planets, galaxies, and a large-scale cosmic web. Not only that, but in at least one relatively unremarkable corner of this universe, a planet arose some 4.5 billion years ago where life survived and thrived. Eventually, it gave rise to an intelligent, self-aware species that can ask deep questions about the universe they inhabit. In doing so, we're also asking fundamental questions about our own selves, as we're just as much a part of this universe as any inanimate objects that exist. We all know that nothing comes from nothing. For something to exist, there must be material or a component available. And for them to be available, there must be something else available. If we put this into a galactic context, an exciting question arises: how could the universe literally come into being from nothing? Where did the material come from that created the Big Bang, and what happened in the first instance to create that material? Join us as we dig deep into the biggest questions of all about our ultimate: how could the Big Bang arise from nothing? Origins. Today, when we look out at the universe, the full suite of observations we've collected, even with the known uncertainties taken into account, all point towards a remarkably consistent picture. Our universe is made of matter rather than antimatter, obeys the same laws of physics everywhere and at all times, and began, at least as we know it, with a hot Big Bang some 13.8 billion years ago. It's governed by general relativity, expanding and cooling, gravitating, and dominated by dark energy, 68%, and dark matter, 27%, with normal matter, neutrinos, and radiation making up the rest. Today, it's full of galaxies, stars, planets, heavy elements, and, in at least one location, intelligent and technologically advanced life. These structures weren't always there, but arose as a result of cosmic evolution. In a remarkable scientific leap, 20th-century scientists reconstructed the timeline for how our universe went from a mostly uniform universe devoid of complex structure to the structure-rich universe we observe today. If we start from today and step backward in time, we can ask where any individual structure or component of that structure came from. For each answer, we can then ask, okay, but where did that come from, and how did that arise? Going back until we're forced to answer, we don't know. At least not yet. Then, at last, we can contemplate what we have and ask, how did that arise, and is there a way that it could have arisen from nothing? So, let's get started. The life we have today comes from complex molecules, which must have arisen from the atoms of the periodic table, the raw ingredients that make up all the normal matter we have in the universe today. The universe wasn't born with these atoms. Instead, they required multiple generations of stars living and dying, with the products of their nuclear reactions recycled into future generations of stars. Without this, planets and complex chemistry would be an impossibility. In order to form modern stars and galaxies, we need gravitation to pull small galaxies and star clusters into one another, creating large galaxies and triggering new waves of star formation. This required pre-existing collections of mass created from gravitational growth, which required dark matter halos to form early on, preventing star-forming episodes from ejecting that matter back into the intergalactic medium. This required the right balance of normal matter, dark matter, and radiation to give rise to the cosmic microwave background, the light elements formed in the hot Big Bang, and the abundance patterns we see in them. These required initial seed fluctuations, density imperfections to gravitationally grow into these structures, which require some way of creating these imperfections, along with some way of creating dark matter and creating the initial amounts of normal matter. These are three key ingredients that are required in the early stages of the hot Big Bang to give rise to the universe as we observe it today, assuming that we also require the laws of physics and spacetime itself to exist, along with matter and energy itself. We probably want to include those as the necessary ingredients that must somehow arise. In short, when we ask whether we can get a universe from nothing or not, these are the novel, hitherto unexplained entities that we need to somehow arise. To get more matter than antimatter, we have to extrapolate back into the very early universe, to a time when our physics is very much uncertain. The laws of physics, as we know them, are in some sense symmetric between matter and antimatter. Every reaction we've ever created or observed can only create or destroy matter and antimatter in equal amounts. But the universe we had, despite beginning in an incredibly hot and dense state where matter and antimatter could both be created in abundant copious amounts, must have had some way to create a matter-antimatter asymmetry where none existed initially. There are many ways to accomplish this, although we don't know which scenario actually took place in our young universe. All ways of doing so involve the following three elements: an out-of-equilibrium set of conditions, which naturally arise in an expanding, cooling universe, a way to generate baryon number-violating interactions, which the Standard Model allows through Sperrin interactions, and beyond the Standard Model scenarios allow in additional ways, and a way to generate enough C and CP violation to create a matter or antimatter asymmetry in great enough amounts. The Standard Model has all of these ingredients, but not enough. If you consider a matter or antimatter symmetric universe as a universe with nothing, then it's almost guaranteed that the universe generated something from nothing, even though we aren't quite certain exactly how it happened. Similarly, there are lots of viable ways to generate dark matter. We know from extensive testing and searching that whatever dark matter is, it can't be composed of any particles that are present in the Standard Model. Whatever its true nature is, it requires new physics beyond what's presently known. But there are many ways it could have been created, including from being thermally created in the hot early universe and then failing to completely annihilate away, remaining stable thereafter. Like the lightest supersymmetric or Cusack-Klein particle, or from a phase transition that spontaneously occurred as the universe expanded and cooled, ripping massive particles out of the quantum vacuum as a new form of a neutrino, which itself can either mix with the known neutrinos or as a heavy right-handed neutrino that exists in addition to the conventional neutrinos, or as a purely gravitational phenomenon that gives rise to an ultramassive particle. Why is there dark matter today when the remainder of the universe appears to work just fine early on without it? There must have been some way to generate this thing where there wasn't such a thing beforehand. But all of these scenarios require energy. So then, where did all that energy come from? What happened before time began? If everything that happens can be attributed to a cause, what caused the universe? To deal with the very tough question of the first cause, religious creation myths use what cultural anthropologists sometimes call a positive being, a supernatural entity. Since time itself had a beginning at some point in the distant past, that first cause had to be special. It had to be an uncaused cause, a cause that just happened with nothing preceding it. Attributing the beginning of everything to the Big Bang begs the question, what happened before that? That's a different question. When we are dealing with eternal gods, timelessness is not an issue. They exist outside of time. But we don't. For us, there is no before time. Thus, if you ask what was going on before the Big Bang, the question is somewhat meaningless, even if we need it to make sense. Stephen Hawking once equated it with asking what's north of the North Pole or, in another way, who were you before you were born? St. Augustine posited that time and space emerged with creation. For him, it was an act of God. Of course, for science, scientifically, we try to figure out the way the universe was in its adolescence and infancy by going backward in time, trying to reconstruct what was happening, somewhat like paleontologists. We identify fossils, material remnants of long-ago days, and use them to learn about the different physics that was prevalent then. The premise is that we are confident that the universe is expanding now and has been for billions of years. Expansion here means that the distances between galaxies are increasing, galaxies are receding from one another at a rate that depends on what was inside the universe at different eras, that is, the kinds of stuff that fill up space. According to cosmic inflation, our leading theory of the universe's pre-Big Bang origins, it really did come from nothing. This requires a little bit of an explanation and is what is most frequently meant by a universe from nothing. When you imagine the earliest stages of the hot Big Bang, you have to think of something incredibly hot, dense, high energy, and almost perfectly uniform. When we ask how did this arise, we typically have two options. First, we can go the Lady Gaga route and just claim it must have been born this way. The universe was born with these properties, which we call initial conditions, and there's no further explanation. Theoretical physicists call this approach giving up. Or we can do what theoretical physicists do best, try and concoct a theoretical mechanism that could explain the initial conditions. We tease out concrete predictions that differ from the standard prevailing theory's predictions, and then go out seeking to measure the critical parameters. Cosmic inflation came about as a result of taking that second approach, and it literally changed our conception of how our universe came to be. Instead of extrapolating hot and dense back to an infinitely hot, infinitely dense singularity, inflation basically says, perhaps the hot Big Bang was preceded by a period where an extremely large energy density was present in the fabric of space itself. This caused the universe to expand at a relentless inflationary rate. And then, when inflation ended, that energy got transferred into matter and antimatter and radiation, creating what we see as the hot Big Bang, the aftermath of inflation. In gory detail, this not only creates a universe with the same temperature everywhere, spatial flatness, and no leftover relics from a hypothetical grand unified epoch, but also predicts a particular type and spectrum of seed density fluctuations. We then went out and saw these from just empty space itself, although it is empty space filled with a large amount of field energy. A natural process has created the entire observable universe, rich in structure as we see it today. That's the big idea of getting a universe from nothing. But it isn't satisfying to everyone. To a large fraction of people, a universe where space and time still exist along with the laws of physics, the fundamental constants, and some non-zero field energy inherent to the fabric of space itself, is very much divorced from the idea of nothingness. We can imagine, after all, a location outside of space, a moment beyond the confines of time, a set of conditions that have no physical reality to constrain them. And those imaginings, if we define these physical realities as things we need to eliminate to obtain true nothingness, are certainly valid, at least philosophically. But that's the difference between philosophical nothingness and a more physical definition of nothingness. As Ethan R. Siegel, an American theoretical astrophysicist and science writer, wrote in 2018, there are 4 scientific definitions of nothing, and they're all valid depending on your context. A time when your thing of interest didn't exist, empty physical space, empty spacetime in the lowest energy state possible, and whatever you're left with when you take away the entire universe and the laws governing it. We can definitely say we obtained a universe from nothing if we use the first 2 definitions. We cannot if we use the third. And quite unfortunately, we don't know enough to say what happens if we use the fourth. Without a physical theory to describe what happens outside of the universe and beyond the realm of physical laws, the concept of true nothingness is physically ill-defined. In the context of physics, it's impossible to make sense of an idea of absolute nothingness. What does it mean to be outside of space and time? And how can space and time sensibly, predictably emerge from a state of non-existence? How can spacetime emerge at a particular location or time when there's no definition of location or time? Without it, where do the rules governing the fields, and particles both arise from? This line of thought even assumes that spacetime and the laws of physics themselves weren't eternal when, in fact, they may be. Any theorems or proofs to the contrary rely on assumptions whose validity is not soundly established under the conditions we'd seek to apply them. If you accept a physical definition of nothing, then yes, the universe as we know it very much appears to have arisen from nothing. But if you leave physical constraints behind, then all certainty about our ultimate cosmic origins disappears. Unfortunately for us all, inflation, by its very nature, erases any information that might be imprinted from a pre-existing state on our observable universe. Despite the limitless nature of our imaginations, we can only draw conclusions about matters for which tests involving our physical reality can be constructed. No matter how logically sound any other consideration may be, including a notion of absolute nothingness, it's merely a construct of our minds. And that also leads to a mind-blowing idea: there is a whole universe in your brain. But did you ever think that your brain could be a reflection of the vast universe out there? The network of neurons in the brain and the network of galaxies in the cosmos might actually be reflections of each other. This is what you get when you put the minds of an astrophysicist and a neurosurgeon together. Besides being two of the most complex systems in nature, the number of neurons in your brain is eerily close to the number of galaxies in the observable universe. Neurons form in long filaments or nodes between filaments, just like galaxies. And there is mass or energy that has seemingly passive roles in both water and the brain versus dark energy in the void of space. Unlikely as it seems, astrophysicist Franco Vazza and neurosurgeon Alberto Faletti, who